All right, so this is the last big idea of our Unit 7 packet, and we're going to be digging a lot more into that redox application that we mentioned earlier in the unit. And this is going to cover pages 16 and the top half of page 17 in your packet, and we'll pick up from there in class, getting into that half reaction thing and finishing up our packet. So, first, remember from what we talked about earlier in our application section, redox reactions are all about changes in charge. An element is going to have a change in their oxidation number, and the oxidation numbers are very similar to and kind of related to the charge. And so the end of that blurby-do at the top of the page is really where it kind of mentions that redox reactions have changes in oxidation numbers, and technically the sum of the oxidation numbers is equal to the charge. And that's really what we're going to be focusing on, is understanding how these things are related today. So that table that's right underneath that first top paragraph is really where this is going to come into play. So if we have a single element, something like Na, or even a diatomic element like O2, something that's all by itself with no other element, and that element doesn't have a charge written on it, then its oxidation number is 0. It has no charge, it has no oxidation number, otherwise we would see it. And that's what you see in this second row, monatomic ion. Mono means one, so this is a single atom that is an ion. And that ion will always have to have that charge written in that top right corner. If you see a charge written there on a single atom all by itself, then that charge is equal to its oxidation number. Now, technically, there are some other general rules about some special elements that like to have certain oxidation numbers, but I'll be honest, the most important thing for you to remember, if it's not a single element by itself, like what those first two rows talk about, a single element by itself with no charge is 0, with a charge, oxidation number is equal to the charge. Everything else is going to have elements together in a compound. And the most important rule to remember when we have elements together in a compound and we're trying to find the oxidation numbers is that in compounds, the last element in the compound always gets the oxidation number that matches its charge from the periodic table. I think of this kind of like the youngest, last child in a family, the baby of the family always gets whatever it wants, whatever they want. At least that was my perspective. I was one of the older children in my family, and it always felt like my little sister, my baby sister, was always getting whatever she asked for. So the same kind of thing happens in compounds. The last element in any compound gets what it wants, gets the periodic table charge that it wants to be stable and happy. And it's those first couple of elements that are going to have to kind of balance that last one out. They're going to have to deal with whatever is left over from that last element. So we're going to do some example problems that'll hopefully make a little bit more sense. But like we said up above, the sum of our oxidation numbers is always going to be equal to our charge when we have more than one element together. And in a neutral compound, kind of like with a neutral element, if there's no charge written on that compound, the total charge is going to be 0. If we do have a polyatomic ion, something that is a group of atoms that have a charge, then the sum of those oxidation numbers has to equal that charge. So a lot of words here, but I think this is all going to make more sense if we put this into play with some examples. So I've kept the key ideas that I just mentioned on that last page here while we look at these examples. And the first couple of examples are pretty easy. If we just have single calcium here, it's a single element, nothing written up in the top corner, then the oxidation number of this atom is going to be 0. Similarly, here with this copper ion, I see a charge up here in the corner. So that charge is going to be equivalent to its oxidation number. So that copper has a +2 oxidation number. Here, remember, diatomics aren't special or different. This is still just a single element because it's just H, no other element there to hide or kind of combine with that oxidation number. So if we don't see a charge on that H, even as the H2 group, that means that it has 0 as its oxidation number. Now, you're not going to see this much, but I could just tell you a chloride ion. And so I know chloride is Cl, and I could look at the periodic table. Since this is just a single element by itself, if it is an ion, it's going to have a charge of -1. And because that's a single ion with a -1 charge, that means that its oxidation number is also going to be -1. I'm actually going to write it this way so that you can clearly see. These red numbers are my oxidation numbers that we're answering. And it's really only when we start getting compounds that we have to dig into it and think a little bit harder about what the oxidation number would be. And so this is where what I said right here, the last element always gets the oxidation number that matches its charge. Well, the last element here is chlorine. And like we just said before, chlorine likes to be a -1. So that chlorine gets whatever it wants. It gets to be a -1. In fact, both of them get to be a -1. And now copper has to have an oxidation number as well. And because these are together in a compound, the total of the oxidation numbers together, the copper plus those two chlorines, needs to add up to the charge on that compound. And since there's no charge written here on CuCl2, not like what we have here, this NH4 group has a total +1 charge, CuCl2 doesn't have a charge written on it, which means the total is 0. So we have to ask ourselves, what is the charge of copper? That one copper with whatever its charge, its oxidation number is, will add up with those two chlorines that are both -1 to equal 0. And this is where you might remember back in our naming unit, I like to draw some little kind of scales here to help you visualize this balancing. And in fact, this is a problem just like what we were working back in that naming nomenclature unit. It's a transition metal. In order to write this name, in order to call this copper something chloride, we'd need to find what that Roman numeral is in the name by finding copper's charge. So we give the last element whatever it wants, and we have two chlorines there, which means we have a total -2 charge in our compound. What is copper going to have to be so that that total will add up to 0? Well, +2. So copper's oxidation number is a +2. Each of those chlorines is a -1. So same process as what we've done before. I know some of y'all struggled with that though, so we're going to practice that again now. And like I pointed out with this next one, the NH4 plus, this time the charge isn't going to add up to 0 because this has a total charge of +1. But the process is still the same. I'm going to draw this here on my scales just to kind of prepare for this problem. This NH4 plus has 1 N and 4 H's, and the total charge is going to be +1. Now, if we give the last element whatever it wants, we look at the periodic table. What charge does hydrogen want? +1. So each of those hydrogens has a +1 oxidation number. And I'll go ahead and write that above my original compound here as well. And if our total positive charge over here is a +4 from all of those red +1s here, and I know my total of my N's oxidation number, whatever it is, plus the +4 from our hydrogens has to equal +1, then what is nitrogen's oxidation number going to be? What plus +4 gives me +1? And that would be -3. So if that nitrogen is a -3 for its oxidation number, that -3 plus 4 +1s will add up to +1. Now, that's not a big surprise because according to the periodic table, nitrogen does want to be a -3. But that's not always going to be the case. Remember, it's only that last element that gets whatever it wants. Sometimes that first element is going to have to make do with some charges that it doesn't really like. And we're about to see that actually in this next example, NO3. So I've cleaned up my scale here and drawn out 1 N and 3 O's. And notice that this has a -1 charge on that NO3. So whatever the oxidation numbers of this 1 N and 3 O's are, it's going to add up to -1. but we always start with the last element. Oxygen gets whatever charge it wants. According to the periodic table, what charge does it want? -2. So each of those oxygens gets a -2 oxidation number. And so that gives us a total -6 in that compound. And whatever nitrogen's oxidation number is has to add up with that -6 to bring us up to -1. So what plus -6 gets us -1? Well, that's going to be a +5. So nitrogen here is going to have to be a +5 oxidation number. So that -6 plus 5 brings us up to -1. And that is very, very different from the -3 that nitrogen would prefer. And so that oxidation number tells us a little bit more about how kind of stable, how happy those elements are in that compound. And nitrogen would much rather be in that ammonium NH4 plus 1 group than in this NO3 minus 1 group. It's very unstable. It's not very unstable. It's stable enough to be a group, but it would much prefer a better group. So I'm going to stop using the scale as much in this big fancy process over here. It helps you visualize things and you can always use it. But I want to kind of show you with these last few examples how it's sometimes a little bit easier to just kind of do that same kind of scale stuff written around the compound, so you don't have to do as much writing and drawing of stuff. So in general, when I look at a compound like this N2O, I just kind of split it down the middle, kind of see both sides of my compound, and I give that last element whatever it wants. So this is a -2. Now, if there was like more than one of those oxygens here, I might bring that down and multiply that number by a certain number of atoms to write down the total at the bottom. But since this is just -2, I'm just kind of bringing the -2 down. Now, in order to cancel out and have this add up to 0, because there's no charge on this N2O, that means that this N side of things is going to have to be +2. But notice there's 2 N's here. And the oxidation number we're talking about is the individual oxidation number of a single nitrogen. So +2 is not the answer here. But we can easily kind of see and think through if the N's have to be the same and they add up to +2, because they've got to, then what is each nitrogen going to have as its oxidation number? Well, a +1. So I kind of do this kind of 4 square situation here when I'm working this out on my own, if I need to show some kind of work to think through it. So same kind of process over here. I've got my O side and my Mn side. We give those oxygens whatever they want, -2. Since there's 2 of them, that means we have a total -4 charge in this compound. And in order to cancel it out, the Mn's are going to have a +4 total. But since there's just one Mn here, that means that the 4 is the charge, the oxidation number, rather, of that manganese ion. And this is a way shorter, way simpler than drawing out a big complicated scale, as long as you kind of remember that you're trying to balance and get that total on either side to add up to 0, or whatever this total is. So let's work another one in this kind of simplified way that has a total charge. So SO4 -2, we're still going to give that last element, that oxygen, whatever it wants, so it gets a -2 oxidation number. There's 4 of them, so that means that we have a total -8 oxidation number here. And in order to add up to -2, that means the sulfur is going to have to be a +6. And there is just one sulfur, so that +6 is the oxidation number of that sulfur. Now, these last 2 are a little bit more complicated looking, but they really aren't that different. The difference that you're seeing here is that we have a polyatomic ion, like this SO4 we were just looking at, with another element. So you'll notice this doesn't have a charge on it, which means the total of all of these elements together is going to add up to 0. The difference is when we're splitting this, we're going to have to split off the last group of atoms here. and give that last group of atoms the charge that it wants. And so we know here that sulfate, this SO4 stuff, is going to want to have a total -2 charge. We can check the back of the periodic table, or we can look at the previous example here. So all of this stuff is going to add up to -2. And we're going to dig into all of that in a second, but still, just like before, we give the end what it wants, and then we have to think through, okay, we have 3 of those -2 ions here. So we have a -6 here, which means that the aluminums are going to have to cancel that out and be a +6 total. And since we have 2 of those aluminums here that both together are going to have to add up to that +6, that means that each of them is a +3 charge. So now we have aluminum's oxidation number taken care of, but we still might need to be asked, if we're told to find the oxidation number of each atom in these compounds, like what it says up at the top, we still need to find the separate oxidation numbers of the sulfur and the oxygen. And so we focus then on that. Ignoring the aluminum, we know that this total charge for a single SO4, we can kind of ignore the 3 at this point, is going to be -2. But we split it in half. Hey, just like what we did over here. Give the last element what it wants. So oxygen's a -2. That's a total -8, which means this, in order to add up to -2, has to be a +6. So just like the last example, we go through the same process, digging in a little bit deeper to find the oxidation number of each piece of that polyatomic ion. So now we have our answers: aluminum's +3, sulfur's +6, oxygen's -2. So when we have a big crazy looking compound with a polyatomic, you still split it into 2 pieces, give the end whatever it wants, and then if there's still multiple things to break down, you just keep breaking it down, giving the end whatever it wants. So we're going to split off this carbonate ion, which is a -2 total charge if we check the back of the periodic table. And so in order to balance out that -2 group, and we just have 1 carbonate here, then this sodium side has to add up to +2. Since we have 2 sodiums, that means each sodium is a +1. Now we go a little bit deeper into this carbonate ion. We know the total. I'm going to change this to green, just so I know it's not the oxidation number. The total for that carbonate ion is -2, but we split it apart and we give the last element whatever it wants. Oxygen is -2. And since I have 3 of them here, that brings our total negative oxidation number to -6. So to add up to -2, if we already have -6, that means carbon is going to have to be a +4. And there is just 1 of them, so that is our oxidation number of our carbon. And cleaning this up a little bit, because this does get a little bit messy sometimes. Sodium's a +1, carbon's a +4, and oxygen is a -2. So we're going to dig in deeper to these oxidation numbers and use them to do some redox reaction stuff. But if this is all that you manage to get from this, like we're going to be practicing as we make things more complicated, this is an important skill for you to be able to do. It builds off a skill we've done earlier. And even if you don't get all the other complicated stuff, this is all you really need to be able to pass at the very basic level. If you want to do more than just pass, well, then stick with me, because we're going to use these oxidation numbers to tell if something is being oxidized or reduced. That's the whole point of a redox reaction. There's always going to be reduction and oxidation happening there. And this tells us if an element has lost electrons, that means the oxidation number is increased. We say it's been oxidized. If an element has gained electrons, the oxidation number is decreased. We say it's been reduced. All of that is written on your page, but remembering all of that is kind of complicated. So there are actually 2 different mnemonic devices that we can use to remember these things. The first one is oil rig, off to the left-hand side there. And oil rig stands for oxidation is losing, reduction is gaining. And that matches what you see in each of those sections. Element has lost electrons, it's oxidation, it's been oxidized. But right now with that just oil rig, it says oxidation is losing, reduction is gaining. But what is it gaining? some people get confused, and you'll notice the oxidation number goes up. Oop, there we go. Goes up, increases when we lose electrons. Because remember, electrons are negative, so less electrons means our charge, our oxidation number is going to be more positive. So sometimes people get confused, even with this oil rig mnemonic, because they forget it's losing electrons, which means oxidation numbers go in the opposite direction. So I like this other one, Leo Gur, and I kind of add a little bit in the middle that helps me remember it. Leo the lion says grr. And what Leo means is losing electrons is oxidation. That helps me remember what I'm losing. I'm not losing charge or oxidation numbers. I'm losing electrons. And less electrons means more positive. So I really like the Leo the lion says grr situation. Because it helps me remember more of the details and remember a little bit better how to figure it out. But it's up to you, or, come up with your own different mnemonic device to remember this oxidation and reduction stuff. But this is why we're finding all of those oxidation numbers. And if you look at the top of page 17, I brought that Leo Gur up to the top to remind you of what these means. When we look at elements in a reaction form, they're going to be changing oxidation number. So we're going to be looking at things and saying, oh, copper on its own, that's 0. Over here, chlorine gets to be a -1. Copper is forced to be a +2. And so that means the copper is going from a 0 before the reaction to a +2 oxidation number. So it's going up in oxidation number, which means that it is losing electrons. So copper is being oxidized. If we look at this next one, silver on its own is 0. I always start with the easiest, most obvious part. Now silver is in a compound, and bromine gets whatever it wants in that compound. Silver is forced to cancel it out, balance it out. That silver has a +1. So from before the arrow to after the arrow, silver's going from +1 to 0, which means its oxidation number is going down, getting more negative, so it has more electrons. It's gaining electrons. So according to Leo the lion, we are being reduced. And this is honestly more of what I remember. Electrons are important and everything, and we're going to get more into how and why they're important a little bit later. But when we see this reducing, the oxidation number goes down. So that's what I always remember, because we're going to be looking at oxidation numbers as much as, if not more than electrons. I look at that oxidation number and the fact that it's going down, and I can always remember reduced means going down. Just like if I reduced your score on a test, it's going down. I reduce your salary, I reduce anything, that means it's going down. So oxidation is kind of a weird random word you might not have ever used before, especially not in daily life. But reduced is a normal-ish word, and reduced means going down in every sense of the word, and that's what it's doing to our oxidation number here. The oxidation number is going down. So that's kind of the last key idea we're going to talk about. I just want to look at each of these. I'm going to go ahead and give you the oxidation numbers for everything but that number 3. I'm going to ask you to try and find those oxidation numbers and do your best to figure out who's being oxidized and reduced here. I think that one's the level that I want you to be at walking in the door, and if you're not there, we'll work on it. But I do want to go through these other 3 examples with you just to help model what I'm expecting. So here, because we need to look at each element and how it's changing. And sometimes kind of drawing that line can help you see, okay, zinc is going from 0 to +2. Figuring out if it's oxidized or reduced. And the one thing I know is reduced means going down. Is zinc going down? No. It's going up from 0 to +2. So it's not being reduced, which means zinc is being oxidized. If we look, copper, on the other hand, is going from +2 to 0. That is going down. It is being reduced. And if you notice, that chlorine is a -1 ahead of the reaction before the arrow and -1 after. So it's not being oxidized or reduced. There's always going to be one element of each. And that chlorine is going to be called what we call a spectator. And it might actually not end up being in our final reaction at all. It's kind of a weird situation. But we'll talk about it more in class. So here, magnesium 0 to +2, that's going up. So that means magnesium is being oxidized. And our oxygen going from 0 to -2 means oxygen is being reduced. It's going down. Now this last example, let's see, aluminum is going from +3 to +3. Nope. Chlorine, -1 to -1. Nope. Sodium, +1 to +1. Nope. Iodine is -1 to -1. Like, nothing here is changing. There's no oxidation number changes here. Any idea why that might be? Nothing is being oxidized or reduced. And if you remember back when we were talking about redox as an application, you remember that not every single type of reaction is a redox reaction. There's one exception, one type of reaction that is never redox. And this is that type of reaction. This is a double replacement reaction. And double replacement is never redox. Actually, I'm just going to write, like I just said, is never going to be redox. So, the good news is you're never going to have something quite as big and complicated like this to find oxidation numbers of, because if we did, it'd just be an exercise in making you miserable and finding lots and lots of oxidation numbers, because we can't do anything with that if no oxidation numbers are changing. We can't pull things apart in that half reaction method that we're about to be doing. So that is the end of this podcast. I know it was a little bit longer, but this is a really important idea that we're going to grow on next class. So make sure to finish this up. It's the only thing I'm asking you to do on your own here. Find your oxidation numbers, try and figure out who's being oxidized and reduced, and we'll see if you're ready to move forward next class.